So hello students. So today in this session, we are going to talk about the evolution of probabilities associated with our hypothesis. So in the previous class, we have seen the brute force MAP learning algorithm. So how? So we are going to apply the concept of brute force. We are going to find maximum a posterior hypothesis. So today, evolution of probabilities associated with the hypothesis. It's a very simple concept. Let us try to understand when we have different hypotheses, how the probability we are associating, because we have seen that in our Bayes theorem, pre-error probability is very important for us. So you have to identify or calculate the pre-error probability. So now what we told, if you don't have the domain knowledge or the domain expert, so now how we are going to assign the pre-error probability, and we told that equal probabilities. So we are going to assign equal probabilities to all the hypotheses in our set of all hypothesis space. So that's what we are going to see here. Now initially all hypotheses have the same probability because we don't know, we don't have a domain expert or the knowledge. So whatever hypothesis we are having for all hypotheses, now we assume the same probability. Now as the training data accumulates, so once you start getting the training data, once you start collect the training data, so then the posterior probability for inconsistent hypothesis becomes 0, right? So when you get the training data and when you calculate the posterior hypothesis or posterior probability for that particular hypothesis, right? So for the given data set or the given training set, now whichever hypothesis is consistent, now the probability for such hypothesis start increasing, and the probability for those hypotheses which are not consistent, it starts decreasing and it becomes 0. So that while the total probability when you are going to sum up, it will be equal to 1. So now this can be seen with respect to this particular example. Now if you look this particular diagram, so okay, so now you just see this particular first diagram. Now here on the x-axis we are considering the hypothesis, and y-axis we have got the probability of the hypothesis. Now initially, suppose say that you have some hypothesis, say for example you have hypothesis H1, H2, H3, H4, 4 hypotheses there in our set of all hypothesis space, right? So here 1, 2, 3 and 4. Now initially for all these hypotheses you are assigning the same probability, equal probabilities, right? So we are assigning equal probabilities, so the diagram looks like that. Now after certain period of time, let us say that you have collected a data training example data set, let us say D1, you collected some 1000 data set, and now when you calculate the probability for this hypothesis H with respect to this data set, now what has happened is some hypothesis, it may not be consistent with the given data set. Now assume that H1 hypothesis is not consistent with this data set D1, then what happens is the probability start decreasing, or we can say probability becomes 0 for all the 1000 data set. Let us say H1 is not consistent. So similarly H2, H3, and you can even say that H4. Suppose we take another hypothesis H4. Now it is also not consistent, so its probability reduces. Now initially for all four hypotheses we have given equal probabilities. Now when you took one training example data set D1, now for that particular data set, now you can see here y-axis what we have written, probability of the hypothesis given for this data set D1. So when you take one set of training examples, so let us say you have collected 1000 training examples, now some hypothesis will drop out. So we will drop out that hypothesis because the probability becomes 0. It is inconsistent with the given data set, right? So now in this case, let us say the two hypotheses H1 and H4 we have dropped out. Now after certain period of time, you collect another 1000 records. So first already you collected 1000 data points and you are calling it as set D1. Now then you collect another 1000 data points, you call it as D2. Now as the training example increases, now once again now you have two data points here. So now you can see here D1 and D2. So we have two data points, right? D1, that is set of all data points D1 and D2. When you calculate the probability now with respect to both of these, now let us say H3, hypothesis H3 also drops out. So now you are left with, let us assume that this is H2 hypothesis. Now H2 hypothesis becomes more consistent. The remaining three hypotheses becomes inconsistent, so we are leaving that hypothesis. So this is how now we can say that as training data increases, right, as the training data increases, the posterior probability of inconsistent hypothesis becomes 0, while the posterior probability increases for the hypothesis remaining in the version space. Whichever hypotheses are consistent, the probability keeps on increasing. Whichever hypothesis, it keeps on decreasing. So initially we don't know anything, so we just assume that all probability with all the hypotheses with the same probability. Then we start collecting the data points, and with respect to that data points, when you are going to calculate the probability, so then you can see that the posterior probability increases for those hypotheses which are consistent. That is how we can say that evolution of our probabilities. So now we will look into the another concept, how MAP hypothesis and consistent learners. So if you want to have a consistent learner with respect to your most a priori probability hypothesis. So now we are trying to understand here. Now every hypothesis consistent with D. So when you say that a hypothesis is consistent with D, so now you can see in this previous example now, when you have collected the data sets, so we came to know that H2 out of 4 hypotheses, H1, H2, H3 and H4, hypothesis H2 is probability is more. So we can say maximum a posterior hypothesis. Now out of 4 hypotheses, which is your maximum a posterior hypothesis? H2, because the probability is more for that, right? So now every hypothesis which is consistent with D is a MAP hypothesis, right? Now we will say that any learning algorithm is consistent learner. So when you say algorithm is a consistent learner, provided it outputs, so when that learning algorithm, when it gives an output, which outputs a hypothesis that commits 0 error over the training example. That is what ultimately required for us, right? Any learning algorithm, whenever it is going to give an output, and when you try to look into that errors, so you know that your errors is there. Say you wanted the target value is 50 and you predicted 48. So now there is some error in between. Now you have to see that you have to reduce that error, right? So you have, when you have learned the neural network or back propagation algorithm, what we are doing, you try to keep on adjusting the weight such that this error from 48 it should go to 50, because 50 is your target and your observed is 48. Or suppose say that your target is 50 and your observed value output of your learning algorithm it is giving 55. So it is greater. Again you have to decrease the error. So when you can say that learning algorithm is a consistent learner, provided it outputs a hypothesis that commits 0 errors. So the errors should be as small as possible, or 0 errors for your given training example. Now given this above analysis, so now we can conclude that with this we can say that every consistent learner outputs a MAP hypothesis, right? Because it is going to reduce the error, so which is having maximum probability, obviously that will be your MAP hypothesis. So we can conclude that every consistent learner outputs a MAP hypothesis. And if we assume a uniform prior probability distribution over H, and if you are going to assume that you have got a uniform probability distribution, but all hypotheses are assigning the uniform probability, in that case what happens, then the probability of any hypothesis Hi will be equal to Hj for all I, j, right? So if you take 4 hypotheses H1, H2, H3, H4, for all 4 you are given equal probabilities, so then we can say probability of H1 will be equal to probability of H2, or probability of H1 is equal to probability of H4. So that is probability of Hi is equal to probability of Hj for all I, j, and if we assume deterministic, right? Deterministic. So we have two words here, one is deterministic and non-deterministic. Non-deterministic means random, you cannot determine. Deterministic means you know what is the output you are going to get. Say for example, now if I toss a coin, can you tell what will be the output 100% accurately? Can you tell? You cannot tell. Why? You don't know. You cannot predict. You can say probability of getting head when I toss a coin 1 is this much, but you cannot tell exactly. So that is what we can say, it is non-deterministic example, because you cannot deterministic, you cannot say what will be the output. So if you assume that your experiment are such that it is deterministic, you know this is the output what you are going to get. If it is deterministic, noise free training example, right, there is no noise involved in your training example, in that case then how we can write probability of D for the given data set D given H for a given hypothesis. The probability of data set for this given hypothesis we can say is equal to 1. We can say it is equal to 1 if D and H are consistent. Right? If hypothesis is consistent with respect to this given data set D, so then if it is deterministic and noise free, then we can say that the probability, posterior probability of D given for that particular hypothesis is 1. Otherwise, we can say it is 0 otherwise. Right? So now this is what now we have tried to understand with maximum a posterior hypothesis, and we have seen the brute force algorithm and how when we say that our machine learning algorithm is a consistent learner means obviously, so you are going to have a MAP or most likelihood hypothesis. So now we will try to look the maximum likelihood and least square hypothesis. Now we will try to understand the link between maximum likelihood hypothesis. Already we have discussed that in our previous section. So from maximum a posterior hypothesis, now how we came to maximum likelihood hypothesis, right? So now that maximum likelihood hypothesis and least squared error hypothesis. Now how we are going to reduce that error? So this concept we are going to understand here. Now let us consider a problem of learning a continuous valued target function. Continuous value target function. So continuous value target function means what? Say for example, you want to predict the price of a car. So you have got lot of machine learning algorithms or applications are there. So second hand car you want to sell it in the market, but before selling you don't know at what price you might sell this car. So based on certain features, now you are going to sell that car. So that output, so you may be selling it for 1 lakh, 1,10,000, 1,20,000. So different. That is continuous value. It is not discrete. Discrete means either yes or no, either true or false, 0 or 1. That is discrete. Now if you consider problems such as continuous value target function, when your target function is continuous, or predicting the share market, predicting the stock market or the housing price, right? Now these are all some of the examples which you can see for a continuous value target function. Or take a problem which is faced by many learning algorithms, wherein which such as wherever you are using the neural network, linear regression, polynomial curve fitting. Now all this where the continuous value target function comes into the picture. Now if you consider such a type of a problem, and so a straightforward Bayesian analysis will show that under certain assumption, any learning algorithm that minimizes the squared error, between the output hypothesis predictions and the training data will output a maximum likelihood hypothesis. What is the meaning of this statement? So whenever you consider such a type of continuous value target functions, now any learning algorithm, if you apply our Bayesian analysis with certain assumptions, now we can see that any learning algorithm that minimizes the squared error. See why we are using that square? You know that when you are taking certain examples or data points, you know what is the target value and what the observed value you are going to get, right? So now if the observed value and the target value, if it is equal, no error. But if there is a difference, see sometimes if assume that you are supposed to get target is 50, 50 points, say, or we can say the total number of defaulters in a bank, some analysis you have done and it is giving that. So your 50 is the customers in our bank who has not paid the loan amount till now. So 50 members are there. Now you try to learn, you with certain data set, now you learn, you build a machine learning model or a program. Now output it is going to give 45. It is telling you that there are 45 people who are not paid the loan, or who will not pay the loan, but your target is 50. So if you find the difference, that is T minus O, 50 minus 45, you got some errors are there. You expected 50 but you got 45. And so, or it may also happen that you may get 55. Target is 50, observed is 55. So now what happens? 50 minus 55, you get negative value. So sometimes you get positive, sometimes you get negative value when you try to find the errors. Now to remove that negative value, so we are going to square the errors. So that is why now you can see here what is given. Where is the cursor? So you can see, minimize the squared error between the predictions, right? Your hypothesis predictions and your training examples. So which will output a maximum likelihood hypothesis, right? So now consider the problem. Now let us consider a problem setting is like this. Now let L is a learner, some module, some algorithm, program, some learning system is there. So this learner L now considers an instance space X. So you have got a set of all instances space capital X and a hypothesis space capital H, which consisting of some class of real valued functions. Real valued functions. Real valued means what? Continuous functions we told. It is not 1 or 0. Right? It is a real value, but you have so many values are there. Defined over this set of all instances X. That is, each hypothesis in capital H, now it is a function of the form. So then we can say, how we can say, for each hypothesis small h, it is a function from the set of all instances X to a real valued function. It gives you then output, which is a real valued function, where R represents the set of all real number. So with respect to certain parameters, say for example, when if you are going to predict a car, second hand car price you are going to predict. Now with respect to certain parameters, that is X, so right, you take one instance. Now for that particular training data instance, so you will be having how many number of kilometers the vehicle has traveled, right? So who is the owner, or how many owners, what is the make of that vehicle, in which year, what is that make. There are so many parameters. Based on all that parameters, your learning program is going to predict that for this car which is been purchased based on certain features, very old, now second hand price or the third hand price, now when you want to sell it in the market, it is predicting that the price of this is 1,25,000. So 1,25,000, that is the output R, real valued function it is going to give. This is how we are going to consider a learning problem now. Now the problems faced by the learner is to learn an unknown target function, right? So now you, based on certain training data set you are given, now a new data set, when a new training example comes, now for that unknown target function F, which is X, set of all X to R, drawn from a hypothesis H. Now that is a problem when an unknown example comes. Now each training example, when you consider here, now you can see that each training example is of a form xi comma di. Xi is a set of all instances comma di. So in our first module and all, we were considering C. C is the output, right? Target value. So here instead of C we are using di. So this is the di. So our training example will be is of a pair xi comma di. Now where what is this di? What is that predicted output of your hypothesis prediction you are going to do? This di is equal to f of xi. So you are going to use, it is a function of this xi. You have got for each training example you have so many parameters will be there. So f of that xi plus some error term ei. So you will be getting a particular error term. So ultimately, what is our goal? This error we have to reduce. So you will be di, you can say that di is equal to f of xi plus ei. Now the task of the learner is to output a maximum likelihood hypothesis. So now the task of our learner is, now you have to output, you have to give an output which is maximum likelihood hypothesis, or in another term we can call it as MAP hypothesis, maximum a posterior hypothesis, assuming that all hypotheses are equally probable a priori. That means we are assuming that all hypotheses are having equal probabilities initially. So now let us take a simple example. Now a particular graph has been given here. So now x-axis and y-axis is there. X-axis is your independent variable and y-axis is your dependent variable, right? So you have got so many parameters are there. So based on that, now your dependent variable y, you are going to get the output. A simple example of such a problem is learning a linear function. Now we call it as a linear function. So you can say this linear function y is equal to, for a linear function, so you know that you will be having some slope and to intercept or certain parameters. So you are going to give some values into x1, right? So some values, some weightage you are going to give through 3 into x2. Now x2 will be the total number of kilometers the vehicle has run. So x2 will be the year, at which year the make of that vehicle. So you assign so many variables will be there, then you calculate and you are going to tell what is, you are going to predict what is the price of that particular vehicle. So such a type of an example when you consider, now what happens, now these dotted data points here, now these are all the data points which have been marked here, right? Now these are the data points in which you have marked, and the target function f corresponds to the solid line. Now what you do, you have to calculate a target function. So now this target function, now you are going to get one, you try to draw a line, so now which is called as the target function. So you are going to draw one particular line. Now when you look into this dot, this particular dark line, so now you can see that all points are not falling on this particular line, right? So all points are not falling on that particular line. So some points are on the top, some data points are on the down. So this is what, now you want to have one particular line, you want to come or you want to draw a particular line such that all these data points either it should fall on that line or at least nearer. Now if you take here, now this is your solid line and your one data point is here, or this is, like say for example, this is your solid line, data point is here. Now there is a difference, there is this much of difference is there. Now that difference we call it as our error term E. Error term E. So the training example xi comma di are assumed to have a normal distribution or distributed noise Ei. So it has got a error term Ei, now with 0 mean added to the true value of f of xi. So that means now you are supposed to find a line, now you have to fit a line now such that this error decreases. Now if you consider this another dotted line, so there are two lines are drawn here. Now if you are going to take another dotted line, that particular line, now if you see here, this is the solid line here and this is the dotted line. If you are able to draw another dotted line, now the difference in error for this data point has decreased. Similarly for this also it decreases, and for this point also, now you can see here, this is solid line, dotted line comes little bit down. That means again the difference has decreased. So like this, now this particular function, now a dotted line function what you have drawn, now we can say that it is a maximum likelihood hypothesis, HML, given these 5 training example. That is how you are going to fit the particular line here, right? So now you can see this is your function f. F is a linear target function, the solid line. Now it has got certain noisy training, or we can say there is some errors are there, and you are going to get a dashed line or dotted line. Now this dotted line we can call it as HML, that is the maximum likelihood hypothesis with least square training error. Now here we have applied that least square hypothesis, we have tried to reduce the error such that the errors with respect to all data points are being reduced. Now before showing why this hypothesis, why a hypothesis that minimizes the sum of squared errors in this setting is called as maximum likelihood hypothesis. So why the hypothesis which reduces the minimum, or which reduces or which minimizes the sum of squared errors, why we are calling it as a maximum likelihood hypothesis? So to understand this, now we will try to look into some of the two important concepts. So the first one is probability density function, small p. So till now we were using capital P for indicating probability. Now we are using another symbol, small p, which indicates probability density function. So we have got probability mass function and probability density function, right? So since we are considering here a continuous variables, for continuous variables, so we have got probability density function. So it comes in the theory of probability. So later on you can do a small research on what do you mean by probability mass function or a PMF and probability density function. Right now you just understand, now we are going to define a probability density function small p for continuous variable, and we have got a normal distribution. So now whenever we are talking about normal distribution, majority of these cases lies in this. So it is a bell curved shape, normal distribution, characterized by with a mean mu. So the mean, so always mean will be at this particular level, and its standard deviation sigma. So the standard deviation, generally if this is the mean, the standard deviation will come around here, which will be so -1 to +1. So it is a bell curved shape. Various example lies here. Suppose say that the life expectancy of the entire population in India. So now we can see that this, you can try to draw a curve like this when you have got all the data points. So that means, so between this year, that is 60 to 70, you can see the life expectancy is more, then it keeps on reduces. So it does not go to 0, because there are certain people will be there who live after 70 years also, but majority comes here, right? So like this examples, majority of the example we say normal distributed. Now if you consider a normal distribution which is characterized with a mean mu, mean is at the center point, and with a standard deviation sigma, then we can state probability density function. So now we are going to define probability density function. Now this is the standard formula which you are considering from the probability chapter. So we can say p, small p of x0 is almost equal to limit as epsilon tends to 0. Now here this epsilon is nothing but a small piece of error, right? So limit as epsilon tends to 0. We want to see that error goes to 0 of 1 divided by epsilon capital P, probability of x0 less than or equal to x less than or equal to x0 plus delta, or sorry, x0 or x0 plus epsilon. So that is a small value of error. So now the probability of this particular function x, which lies between x0 and x0 plus delta epsilon. So this is how we try to define a probability density function. Right now, with this probability, when you are going to define a probability density function, so it's very simple. In very simple, if you want to understand, since we are taking continuous value function, so continuous value target functions we are going to use. So we have to use another function which is called as probability density. Instead of using probability, we are going to use probability density, and that is the equation what we have seen. Now let us now show that the least squared error hypothesis is the maximum likelihood hypothesis within our problem. Now what we have to see? We have to see that the least squared error hypothesis. So least square error hypothesis is the maximum likelihood hypothesis. So it is the maximum likelihood hypothesis. So we shall use small p to refer to the probability density function. Already we have seen that definition. Now we are going to say that HML. So what is this HML subscript ML? This is the maximum likelihood hypothesis. We have seen this definition already in the previous unit. So maximum likelihood hypothesis HML is equal to argument max of all hypotheses belonging to set of all hypotheses into small p, not capital P. It is probability density, not probability. Probability density of all the given data set for the given data, for considering all the data set D given this particular hypothesis. So this is how we are going to say that maximum likelihood hypothesis. So now how we are going to get that? Let us see. Now assume a fixed set of training instances. Now if you consider the set of all training instances x1, x2, x3 up to xm, you have taken some training example and therefore consider the data D. So you have got a set of all training example D. In D, how many examples are there? x1, x2, etc. up to xm. To be the corresponding sequence of target value D. Right? Sorry. So D is what here? D, you are going to represent the target, and capital X is the set of all instances. So capital X has got x1, x2, x3, and you are going to have an output which is considered as a D. So now what is this D? For x1 you will be having one output D1, right? So for another instance x2 you will be having an output D2. Similarly for an instance xm you will be having an output Dm. So now how do you calculate this Di value? So now this Di is equal to f of xi. Already we have seen it is a function of, for all these parameters, f of xi plus ei. So plus small error term ei. Clear? Now assuming the training example are mutually independent. Right? So now assuming that training example are mutually independent. Now mutually independent means, now if you are going to toss a coin, so the tossing a coin, now I can say that it's an example of mutually independent. Now if I toss a coin now one time, assume that I get a head. Second time when you are going to toss a coin, does it depends on the previous output? Since first time I got a head, second time also I will get a head. Does it depends? No. Right? We don't know. Again I toss a coin, I may get head or I may get tail. Does it depends on the previously what output I got? No. That is why, so we can say it's an example of mutually independent. It is not dependent, it is independent. Now assuming that all these training example x1, x2, x3 what you are going, where you are consider, now all these are mutually independent given for a set, for a hypothesis H. Now we can say probability, capital P, probability of the training data set D given the hypothesis H as the product of various small p. Now we are going to use the product. So we are going to use the product because the events are mutually independent. Since the events are mutually independent, we have to take product, not sum. So we are going to take the product of various small p of Di given H. So now we can say H maximum likelihood hypothesis is equal to argmax of product of I for I is equal to 1 to m p of Di. So Di means what? So that is the whatever this particular the data you are going to get, the target values what you obtain for this input given the set of all hypothesis H, right, for this given data set H. So now this P of Di given H now can be written as a normal distribution. So when you try to look into this, now we can try to plot or we can consider this as a normal distribution with variance sigma square and with a mean mu is equal to f of xi. So so you can assume that it obeys a normal distribution which is a bell shaped curve. Now when you consider this as a normal distribution, when you consider that probability density P of Di given hypothesis H obeys normal distribution, then we are going to use one standard equation. From this normal distribution, now the probability density function for a normal distribution is this equation. Again, like how we have seen biased equation, now this is another equation, that is a normal distribution, that is probability density function for a normal distribution. So it is a standard equation, again you have to by heart. So you have to understand now what is this P of x, which is given as 1 divided by square root of 2 pi sigma square into e raised to the power of minus half of x minus mu by variance, standard deviation square, right? So sigma square is the variance, and when you have got a 1 sigma, then it is the standard deviation, so square. So this is the probability density function for a normal distribution. Now since you are considering this P of di given hypothesis as a normal distribution, and for a normal distribution the probability density function is this one. Now we try to bring that here. So now if you look here, what was our equation for HML? That is, the maximum likelihood hypothesis is equal to argmax of product of, for I is equal to 1 to m, P of di given H. Now this we are saying that it obeys normal distribution. This P of di given H obeys normal distribution. Since it obeys normal distribution, now we are considering this equation, that is the standard equation of our normal distribution, and we substitute that in this particular equation. So HML is equal to argmax of H belonging to H, product of I is equal to 1 to m. So instead of P of di given H, so instead of that, now we try to substitute this particular normal distribution. That is the equation of our normal distribution. What is that? 1 divided by square root of 2 pi sigma square into e to the power of minus half 2 into sigma square di minus mu. So now here, now if you see from where we got that di, so because here it is xi minus mu. So what is this x? Now x is the input what we are having. So now this x, since we have got various values of x, so now here we have got di, because we gave the equation that di is equal to f of xi plus ei. Right. So now this value d in place of x here, now we are going to substitute it as di minus mu whole square. So now this is equal to argmax of h belonging to h pi of I is equal to 1 to m, 1 divided by square root of 2 pi sigma square into e to the power of minus of 2 sigma square into di minus now mu. So we are going to, mu is what? Mu is the mean. So mean is nothing but which is equal to h of xi. You are going to find the mean. Now when you have got all the hypotheses are there, so for each xi, for every hypothesis for individual data points, right? So h of xi. So we are going to consider, see we are saying that mean mu is equal to f of xi. That is why, so for each hypothesis h of xi, in place of mu you are going to replace this whole square. Now rather than minimizing the above complicated expression, we shall choose to maximize its logarithm. Now what we do is that, now since this is a very complicated expression, now instead you can reduce this particular expression by applying log. When you apply the logarithm, now we can still simplify this particular expression. So for that particular purpose, so we say h maximum likelihood hypothesis is equal to argmax of h belonging to h. Now we apply log to this. When you apply logarithm, the product becomes summation. So the product becomes summation. Now it becomes sum for I is equal to 1 to m of ln 1 divided by square root of 2 pi sigma square e. E is there, right? So you are applying log. So this is a constant. So you write this constant as it is. When you apply log here, e becomes so minus of this. So minus 1 divided the numerator e to the power of this comes here minus 1 by 2 sigma square into di minus hi h of xi whole square. Now in this, the first term in this expression is a constant. As we told here, this particular term is completely constant, so which is independent of h. So since your argmax says for all hypotheses, but in this first term we don't have any h, so it is a constant independent of h, and since it is a constant, it can be discarded. So we just ignore this particular constant and we get HML equal to argmax of h belonging to h summation for I is equal to 1 to m minus 1 divided by 2 sigma square into di minus h of xi whole square. Since it is a constant, we have ignored that term, right? So now if you look here, now this is a negative term, this is the expression what we got. Now here we have got argmax, that means you are going to maximize this negative term. Instead of maximizing the negative term, so you are going to h maximum likelihood hypothesis is you are going to maximize the negative terms such that your error is becoming 0. Now maximizing the negative term is equivalent to minimizing your positive terms. Understand it carefully. Maximizing the negative quantity is equivalent to minimizing the corresponding positive quantity. So now what we do is, instead of writing argmax here, now we can say HML equal to argmin. So you are going to minimize and we remove this negative symbol. So we are going to remove this particular negative symbol and we say summation I is equal to 1 to m 1 divided by 2 into sigma square di minus h of xi whole square. Is it clear? In the previous equation negative was there and it was argmax. So maximizing your negative quantity is equivalent to minimizing your positive quantity. So we have, instead of argmax, we are going for argmin and we are omitting this negative term and the equation becomes same. So now finally we can again discard the constant, right? Now you can see here, now here we have 1 divided by 2 sigma square, which is a constant, which is nothing related with your hypothesis size. So we can remove or discard this constant in our next equation. So it becomes HML equal to argmin of h belonging to h summation for I is equal to 1 to m di minus h of xi whole square. Now this final equation, this shows that maximum likelihood hypothesis is the one that minimizes the sum of squared errors, right? This is what in our topic we are discussing. So how you see that it is trying to decrease sum of squared errors. Now what is this di? This is the output target value and this is the observed value for all the hypotheses with your given data set and square of that. So we can see that the maximum likelihood hypothesis MHL is one that minimizes the sum of squared errors between the observed training values di and the hypothesis prediction. So observed, so di is what here? Di is the observed training minus your hypothesis predictions. So what are the various hypotheses for each data points what you have predicted, find the difference and square it, and whichever is having minimum value, so in that entire set, so we are going to call it as the maximum likelihood hypothesis. Clear? So now this is what we have understood with the maximum likelihood hypothesis, and how we have seen that the hypothesis which actually reduces the least squared hypothesis is actually your maximum likelihood hypothesis. And there are certain limitations or assumptions which you are going to make here. The analysis, it considers noise only in target value of our training example and does not consider noise in the attribute. Now, what is the main assumption here we are seeing is that in our training data set you should not have any noise free training data set, but noise can be there in your output may be having some noise, but in your training data now the noise we don't have the noise. So this is another, so this section what we have seen. Clear? In the next section now we will be looking into maximum likelihood hypothesis for predicting probabilities, So how we can link this maximum likelihood hypothesis to your predicting probabilities, right? So this concept we will be discussing in our next content. So once again, because this particular content has got a lot of what you can say, it's the equations, the mathematical equation. So kindly go through this once, try to understand this particular topic, and whatever doubt is there, you can just ask me later, so that we'll try to clear. So the thing is, try to read with patience, read once, try to listen one or twice, so then the things becomes more clear. So but the thing is that you have to, starting from the first module, if you are good, if you have got a strong hold, then the next becomes easier and easier. Otherwise the things becomes more and more complicated in our fourth module. Clear? So have a nice day. Thank you very much.